We will continue with the simple design of a processor which we began in the last lecture. What we had done primarily was that we had taken a small subset of instructions and try to design the data path. What we will do today is that we will look at the design from a slightly different angle and come up to the same point. We will then go into details of control part design. So, data path is the one which is doing the computation, and control is the one which guides or directs these computations so that the right action takes place at the right time. This is part of the overall plan. We are looking at a simple implementation where the entire instruction gets executed in a single cycle. After we finish with this, we will look at the performance considerations and probably go for a more involved design, which is a multi-cycle design. So, today we will arrive at the same data path design by looking at it from a different angle. What we will do is we will look at each instruction or group of instructions separately and then try to merge the results or merge the outcome of each separate consideration. And then we will look at what control inputs are required to drive various components in the data path, and based on that we will build the specification of the controller and then go into details of the controller design. We will see one possible implementation using what is called PLA or programmable logic array, and if time permits I will talk of the performance consideration. How do you analyze the performance or analyze the delay of such a design? Okay, at the end we will notice that this particular design approach has some limitations, and once we understand those limitations we will be able to talk of an improved design. Okay, so let us compare the two approaches which I am talking of. One approach we followed in the last lecture and another one we will follow now. What we did yesterday was that we began with one design, let us call that D1, where we looked at 5 instructions which belong to one particular group, namely arithmetic logic group. We augmented or enhanced that design by including store instruction. We improved it further, we expanded it further by including the load instruction. Then we added on BEQ instruction, and then finally we threw in place J instruction. So that is how, starting with a very simple design, we gradually built up more and more involved design, and this process actually can be continued. So you can look at the entire instruction set, look at more instructions, and by following similar approach you can keep on adding or enhancing the design. So that is one approach we followed. What we will do today is that we will look at separate design as if there were only limited number of instructions. So first we will have a design which looks at these 5 arithmetic or logical instructions. Of course, the answer will be no different from what we had earlier, but then we will leave that apart and look at just store word instruction and see what are the requirements for this particular instruction. Similarly, we will do it for LW separately, then BEQ in isolation, then J in isolation, and then we will try to merge these 5 different designs which may have something in common. So that common part will remain common, but we will kind of take a union of whatever are the requirements of different solutions and put them together. So, and since our approach is same, that we are trying to do whole thing in a single cycle and the given broad components have been identified, we will approach the same design point at the end. So this is what we had the starting point even yesterday, that for doing add subtract operation you need PC to supply the instruction address. From the instruction we look at the register address fields, fetch 2 operands from register file, apply them to ALU, result of ALU goes back to register file, and meanwhile we also make sure that PC gets incremented to PC plus 4. So these components can be put together to carry out the first group of 5 instructions. Then now let us look at SW alone in isolation. Here ALU does something different. ALU does the address calculation, okay, and we bring in the data memory component. So ALU feeds the address for the data memory, and the data input, I don't know what happened to the cursor, I am not able to get cursor here. Okay, I suppose you have to live without that. All right, so the address is formed by adding one register content and 16 bits as an offset coming from the instruction. Okay. Next we have data path, portion of the data path, which will take care of LW if that was the only instruction. So notice that now we are still looking at two addresses from the instruction, but while in case of store both were being used to read, now one is being used to read and the other is for writing. It is a load instruction. So one register takes care of address generation and the other address is where the destination of data coming from memory is. This is for BEQ. So again I have omitted data memory. ALU is being used for comparison. Okay, we are looking at two operands from the register file which are being fed to ALU for comparison purpose, and the target address, in case the condition is true, we need to go to some particular target address that's being calculated by adding an offset to PC plus 4, and note that we have sign extension and we have shift by 2 and all those things are there. Finally, for jump instruction, all that we need is putting the right bits together to form the destination address. Right? We don't need register file. This instruction doesn't look at register file, doesn't require ALU, doesn't require memory, and all that you require is some little circuitry to wire the bits forming the address appropriately. Okay, now we have come up with these 5 partial designs. We need to put them together to form the final design. Okay, so these I am calling these as sub designs. We are going to merge these. So this was one. Let's quickly cycle through these. That's the second one for this is for store instruction. Then this is for load instruction. This is for BEQ instruction, and this is for jump instruction. So you would notice that there are a few things common. Each instruction may not utilize all the resources, but if you take union of all these, we can reconstruct the entire design, and that's what we will do now. So we will now okay, now we'll take these 5 as if they were 5 sheets of paper and just superimpose them one over another, and naturally the things which are common will fall in place, and which are not common we'll kind of take union of those. But there will be another thing, that there will be somewhere conflict. In one sub design we want one piece of data to go to a particular destination, in another design we want something else to go to that destination. So we will identify those and take corrective measures. Okay, so the second one is superimposed over the same thing. Third one is again put over that. Okay, so we are not erasing anything, and somewhere the lines are getting doubled up, somewhere two different things will go to the same point. This is for BEQ, and finally this is for jump. So now we have everything just superimposed, and what remains now is to identify the points of conflict where we are trying to send two different things to the same point in two different situations. So, we now try to identify conflicts. This is one point of conflict, okay, where add subtract instructions send one thing here, okay, and the load store instruction try to send something else here, okay. We, in one case we are adding two operands coming from register file, in other case we have one from register file, one is a constant coming from instruction. So, this is a point of conflict. This is another point of conflict in terms of what goes back to the register file. So, in arithmetic instructions, output of ALU goes back, in load instruction output of data memory goes back, and associated with that is this point of conflict, where there are different addresses used to address the write port of the register file, okay. It is either INS 11 to 15 or INS 16 to 20. Different fields in the instruction are addressing the same write port. This is also a point of conflict, where in instructions other than branch and jump, we simply want PC plus 4 to be sent back to PC, but in case of branch we have something else coming out of address calculation, and that needs to be going to the PC. And finally, this point where jump has one way of calculating address, branch has another way of calculating address, and ultimately they need to go to same destination. So, what do we do for these? From the other design, we can actually get an idea that we need multiplexers, and multiplexer will be driven by suitable control signals. So, we introduce multiplexer. Basically, we have to introduce multiplexer and also connect the signal appropriately. So, you would notice that except for one place I have put in the multiplexer. The fifth one, the point of conflict between non-branch and jump instruction and other instruction would get resolved automatically, because the multiplexer we have put for branch itself will take care of that, because it is a conditional branch. It has a provision of passing PC plus 4 as the next address. So, you are either having PC plus 4 plus offset or PC plus 4. So, the provision which we have for PC plus 4 will suffice for non-branch and jump instruction. So, we do not really need a multiplexer there. And let us now remove the conflicting line and put appropriate connections in place of those, and we reach the same design which we had arrived at yesterday. So, just a idea is to give you a different view, different way of looking at it. So, whatever is convenient, that approach could be followed. There is nothing sacred about one or the other. Okay, is there any question at this point of time? All right, if this is okay, let us move towards working on the design of controller. So, you would recall that we had identified control points. So, since it is the same design, we have same points. Primarily we are controlling the multiplexers, we are controlling read write operation of memory, write operation of register file, and we had a gate controlling the PC source, so that the controller design is simplified. So, now what we need to do is look at each instruction or group of instruction and see what value needs to be given to these signals, what inputs need to be given. So, for example, let us start with R type instruction, or basically arithmetic logic instruction. RDST needs to be made 1, because the write port has to be addressed by bits 11 to 15 of the instruction. Okay. So, we need to give this control signal is 1. RW, which tells whether the register file has to take in a new value or not, this also needs to be made 1, because you are writing something into the register file. ALU source is 0, we want to take the top input. MW is 0, we are not writing into memory. MR is 0, we are not reading from memory, and M2R is also 0, because we are taking the bottom input of the multiplexer. Going further, it's not a branch instruction, we keep the signal 0. It's not a jump instruction, we keep this signal JMP also 0. Now let me point out that there is a change which I made in this diagram in relation to the previous one, is this label 10 I have reversed in this jump control multiplexer. Okay, that is just to convenience, so that we have the meaning of this jump signal. The polarity is 1 when it is a jump instruction. I mean, there is nothing very particular about this, but just to call it jump, otherwise I would need to call it jump bar. That is the usual convention. So now this is a set of values, this is a set of inputs you need to give at control points, and if that is given, the instruction done by this data path will be the R type instruction. We still have not specified what input we give to OP. I will take it separately, but let us look at the others for each instruction. So all this put together is this table of values we need to give at different control points, right. Let us go to the next one, SW instruction, and repeat this exercise. RDST is do not care, because we are not writing into register file, and that will be indicated by making RW as 0. So basically, when RW is 0, value of RDST could be anything, it does not matter. ALU source is 1, because we need to take the bottom input. Memory write is 1, it is a store instruction. Memory read is 0, and M2R is also X. This will also go with RDST. So when RW is 0, RDST will be X and M2R will be X. These will be don't cares. It does not matter which one you select. Okay. So as you would be familiar with logic design, that if there are don't cares in the specification, these could be exploited to simplify your circuit. Okay. So from that point of view, we will try to put X wherever we can, and further BRN is 0, JMP is 0. Putting all these together, we have we tabulate all the control signals which are required for this particular instruction. Next is the load instruction, similar exercise. Here we are putting things back into register file. So RDST is 0, we are taking the top input. RW is 1, ALU source, this is same as what we had for store, and now we are not writing memory, but we are reading. Okay. So MW is 0, MR is 1, and M2R is also 1, because output of memory is being sent to the register file. BRN and JMP continue to be both zeros. So these signals can be put together again in the table, and these green table which I am forming, I will have to collate these together to form an overall truth table. Next we move on to BEQ instruction. In BEQ instruction, neither we write into RF nor we read or write from data memory. So those corresponding signals will be 0. RDST is accordingly X, RW is 0, ALU source is 0. We need to take two operands from register file and compare them. MW, MR both are 0, M2R is X, BRN is 1, it is a branch instruction now. So now the Z output of ALU will be brought into consideration, and that together with BRN will control PC source. JMP continues to be 0, okay, and all values put together are in this green table. Finally, we have this jump instruction. So jump instruction again does not require anything with RF, ALU, DM, all these are inactive. So RDST X, RW 0, ALU source is also X now. Since we are not looking at, we are not using ALU, does not matter what you give as input. MW 0, MR 0, M2R X, BRN is also X. Now why it is X? Because once this last multiplexer, this controlled by JMP, where we have made 1, you are looking at upper input, so it does not matter how the bottom input is being computed. You may select any of these, it does not really matter. So this is a set of control inputs for jump instruction. And let's now put these together. Well, this is a just sub table for jump. So we will tabulate the instructions, and against them we will have all the control signals. Okay. So if we put the opcodes of these instructions, from those opcodes we need to derive these control signals, and these two together will form a kind of compact truth table for controller circuit. So, and we know how to once a truth table is given, we know how to design a combination circuit. There are many ways to do it, but I am sure you at least know one. So let's put in the opcodes for these instructions. All R type instructions have 0 as the opcode. Okay, these are arithmetic logical instructions. So this part is common, and that's why we are treating them together. So there are also opcodes I put for SW, LW, BEQ, and J. So what are the opcodes are? We are just taking from whatever definition we have. So there is nothing we are specifying here. This is what is given. Okay. So now here is in the overall design there were 2 control boxes. This is the main controller, and after this now we can look at the second controller which controls the ALU. So as far as this is concerned, we have completed the design up to this point. We have come to the truth table. Okay, now we first define what is how we are encoding OPC. OPC, if you recall, is a signal coming from the main controller and going to the second controller which controls the ALU. Okay, so we said that we will have all instructions falling in 3 categories. R instruction is one category, load store another category, and all the rest are yet another category. Okay, and basically I should say branch is another category. For jump it really doesn't matter. So we need 2 bits to encode those 3 groups, and what we'll do is we'll put in another column here which will define this. So arbitrarily let us choose some code. R type is 10, SW is 00, so is LW, BEQ is 01, and jump it is don't care. So our now the truth table is actually complete. This main controller now, as you can see, has 6 bits as input. Okay, the 6 opcode bits are input for this, and you have 2 bits of OPC plus 8 bits in the other table. Altogether these 10 outputs have to be produced. So it's a 6 input 10 output circuit which we now need to design. But before we do that, let's see what we do with OPC. So we need to look at OPC and the function field in case of R type instructions, and decide 3-bit input control for ALU. So now the group of R type instruction needs to be expanded. We need to consider requirement of each individual instruction. So we repeat this R type entry 5 times because we are considering 5 instructions: add, subtract, and OR, and SLT. So these will differ in terms of their function field. Opcode field is same for these. So the third column shows individual instructions, and the last column shows the function field. The function field is not to be seen for instructions other than R type instructions. Okay, so I just put don't care there, because in those particular bits we have something else. We have address offset or some part of address. They are not specifying function bits. So now for different instruction we need to figure out what input we need to give to ALU. So for the second control circuit, for the ALU control circuit, there are 8 bits of input, 2 bits of OPC and 6 bits of function, and there are 3 output bits which we will decide now by first noticing what is the function ALU is supposed to perform in different instructions. So in the R type instructions the action to be performed is directly given by the instruction. So, add operation for add, subtract for subtract, and so on. For store and load instructions, we also need to perform add operation, and for BEQ instruction we need to perform subtract operation. For jump we need nothing. So, we have enumerated the action required by ALU for these different instructions, and we also we now are in a position to define what control input required for ALU. So, I am recollecting the ALU design. One bit of ALU is being shown here, and you would notice that we need 2 bits to control the output multiplexer. It has to select from one of the 4 possibilities, and 1 bit is actually used to invert B if necessary. Whenever you are doing a subtraction operation, okay, then B needs to be inverted. So, we need to form 1's complement and give initial carry, so that negative of B comes. So, 3 bits are required, and we can I am assuming that the leftmost bit out of the 3 bits is B invert, and the other 2 bits control the multiplexer. So, 0 0 if you want the top input, 0 1 if you want the next input, 1 0 and 1 1. So, therefore, for AND operation, B invert is 0. Actually, one could put it as don't care. Okay, if you are not using the adder part of it, B invert becomes don't care, but I have just put it as 0. So, for AND we are selecting the first or the 0th input in the multiplexer. So, the code is 0 0 0. For OR, I am keeping B invert as 0, and the multiplexer is controlled by 0 1 and so on. So, based on this the way we have designed ALU, we can actually define what is the control input required for this case, and with this our picture is complete, and here we have the complete table. So, this is the truth table for the second controller or the ALU controller, where we have 8 inputs, 8-bit input and a 3-bit output. So, one stage of the design actually finishes here. Now it is a very straightforward, almost a mechanical process, that once you are given a truth table, how do you put down a circuit which will implement that truth table. Given a truth table, you can actually write sum of product expression for it, okay, and put necessary AND gate OR gates. You can also follow other realization, product of sum or NAND or NOR and so on. But one approach which is commonly used in a case like this, when you have multiple outputs, okay, and for control design, typically that is the situation. We follow a PLA based design, where the design is actually derived in a very straightforward manner from the truth table itself. So, the PLA is basically, it stands for programmable logical array. Okay, logic array means that you have a array of gates which are, and this structure is somewhat universal. You can program it to implement any desired function. So, the PLA which will implement this would be fairly large. I will not describe the PLA which will implement this, but I will try to illustrate the basic principle. What is the basic idea behind this approach for design? So, PLA has 2 parts. One is called AND plane and other is called OR plane, which correspond to this. This is basically with AND OR type of implementation or sum of product implementation. So, the AND plane has a row of AND gates, okay, which implement all the product terms, and OR plane has a set of OR gates which implement the sum terms, right. So, the inputs go to AND plane, the output of AND plane is a set of signals representing the products, and the OR plane actually sums those products to form the sum of products. and gives the final output. So the structure, this is the overall outline, and what goes inside the plane is a direct correspondence of what you have put down in the truth table. So let me illustrate. So for a simple situation, let us say you have 3 inputs, call them ABC, and 3 outputs DEF. You have a set of AND gates which would implement the product terms which are required in that implementation, right. So each gate here is capable of taking every input either in true form or in complementary form, right. So now the connection of each gate to the inputs is what is programmable. So if you are talking of M input and N output PLA, then each AND gate will be an M input AND gate. That means it can you can form an arbitrary product of size up to at most M. That means each literal, for example, literals means A or A bar, B or B bar, and C or C bar. So you can form what you see here is that the leftmost AND gate is forming the product A bar, B bar, C. The next one is A bar, B, C bar, and so on. Okay. So in general, you can form product terms which are of less than M inputs also. Okay. So some of these may not be connected, right, and therefore a PLA just needs to form enough number of terms so that all your outputs can be realized, and then you have a row of OR gates which will pick up necessary required subsets of these product terms and sum them. So in this case, D is summing output of all the product terms, E is summing 3 of them, F is summing 1 of them, and this pattern of what gets connected to AND gates, okay, which inputs get connected to which AND gates in what pattern, could be worked out in a very convenient form from the truth table, and similarly which product term go to which OR gate is also very easily derivable. Now in actual practice, the gates don't look like this. These gates are actually what is called wired AND gates or wired OR gates, and in real practice they may not be actually AND gates or gates. You would either have NAND organization or NOR organization, but for conceptually let us continue to think in terms of AND and OR, and the structure may look more like this. Okay. So the top part is the AND plane and the bottom part is the OR plane, where the number of vertical lines, each vertical line represents one product term, and you can see that each vertical line is crossing every input and its complement. Okay. So here you have 3 inputs, and therefore the vertical lines which correspond to AND terms or product terms are crossing all possible input lines and their complements. So you can wherever there is a dot put here, it means that the connection is formed. So given certain number of inputs, outputs, and product term, the overall structure is same. To go from one functional specification to another functional specification, all you need to do is place your dots differently. Okay. You move these dots around, different product term get formed and different product term get summed. So it's a kind of universal or programmable logic, where by placing these dots you can form the required connection and get the required function out. So in actual practice, the AND gates are formed actually vertically, so they are distributed. I am not showing the exact circuit. At each cross point there will be a transistor which you will connect to the cross wire, or you will not connect. Okay. So I suppose we will leave those details to a course on digital hardware design, which you might do later, but just in overall functionality you understand this, that it is a programmable structure which can be automatically generated from the given specification. Okay, having done that, now let's look at what good work we have done. Okay, we have got a design now. How does it fare in terms of performance? So for doing so, we need to calculate the delay and their impact on the overall clock period. So first of all, let's look at the component delays so that we will build it bottom up. We have register, one register in this case PC, for which we will assume that delay is 0. Actually, just to simplify the analysis, we will look at the delay of some prominent component, take them as non-zero, others we will take as 0. So register delay we will assume as 0. Adder delay, now I am referring to the adder which does PC plus 4 and the one which does PC plus 4 plus offset. So let's denote that by T plus. The delay of ALU will denote by TA. Delay of multiplexer will assume again 0. One doesn't have to assume this, I am just doing this to make the expressions or analysis a little simpler. But of course the assumption is a rational assumption in the sense that the delays which are actually small compared to others are being assumed to be 0. Register file TR, program memory TI, data memory TM. Okay. Then finally the bit manipulation components, as again they are only different wirings, we take it as 0. Strictly speaking, even the interconnecting wires will have some delay, and if your gates or the logic is too fast, then wire delay becomes comparable or significant. But again, for simplicity we will ignore that. So now in terms of these parameters, can we determine the clock period? Yes, if we analyze the paths, we can what we will do is, you recall that I mentioned that at one edge of clock you have a new address in PC from where the cycle begins. The data flows through various components and ultimately you write something in the register file or write something in memory and additionally write something in the PC at the next clock. So the clock period has to be sufficient to allow all these informations to propagate to their destinations. Once again, yes.
So what's the difference between register delay and register file delay?
Well, register file is an array, is a collection of registers. Register delay, I am talking of single register like program counter. Okay. Now register file has additional circuitry that you are giving an address, that address is getting decoded, one of the registers is getting selected, and there is some multiplexing at the output end. Okay, so depending upon the size of register file, how many registers it is, it will have some delay. Of course, it's not difficult to see that the delay of memory would be comparatively much more than delay of register file. Okay, and in fact it could be larger by 1 or 2 orders of magnitude. But we will assume that for the moment, assume that the memory is reasonably fast, and it is not. If that was the case, then if you take normal memory, the bulk memory which you have in the processor, and take the access time of register file, we can probably have set everything to 0 except for register file, except for the memory, right? In actual practice, what would be influencing the clock period of a processor is not the main memory but a cache memory. Okay, so we will worry about those details later. At the moment, let's assume that the way we have been designing, we have put memory as part of the processor design, right? So which is an oversimplification, but let's assume that it is the same technology which has been used to build other components of processor and the memory, and all the delays are comparable. So the way I am looking at it now in this analysis is that all the parameters which I have put as non-zero are somewhat comparable. Okay. So we will again, to simplify the problem, look at each instruction or group of instructions separately, see what is the demand on time placed by those instructions, and then put the results together. So if you were to consider add, subtract, and or these instructions, then there are two paths we need to worry about. A path which is computing the sum or difference or and or, which goes through instruction memory, register file, ALU, and back to register file. Okay, so there TI plus TR plus TA plus another time TR. These will get cascaded, so all these get summed. Other path is going through the adder to compute PC plus 4. Okay, so now if I am saying that all are comparable, then the first one is actually meaningless. I could straight away neglect that, and the second expression will dominate. But let me be a little open here and say that the clock period is max of these two. The reason why I want to keep T plus in picture is that as far as ALU is concerned, since ALU time is getting summed with other things, I will have to attempt to make this ALU very fast, otherwise things will be bad. So it is typically in the ALU I will put carry, look, add logic and stuff like that, whereas the other adder has much more room, much more let's say cushion. So I can afford to have a slower adder here because that's going to cost me less, right? And so therefore T plus could be I can afford to have T plus larger than much larger than TA, right? You would recall that the delay in carry, look, add addition and delay in carry, propagate addition, they could differ quite vastly. One is proportional to n, other is proportional to log n, so difference could be large. For SW, what comes into picture is TI, TR, TA, and then TM. Now incidentally here I am assuming the same time for reading and writing, both in case of memory and in case of register file. In general they need not be same, but again just to keep things blowing out of proportion, I am just using same value for each. Okay, so T plus again remains another path. For LW, the chain seems to be longest: TI, TR, TA, TM, and again TR. Okay. For branch, there are three paths I need to consider. One goes through both the adders, so T plus and T plus. Another path goes through TI, the instruction memory, from where we are picking the offset and then adding it to PC plus 4. So it is TI plus T plus. Okay, and the third one where comparison is being done is TI, TR, and then TA. So whichever is the largest of these will dominate. For jump it is T plus or TI. Okay. Now let's put basically now what we will say is that the clock period has to be large enough to accommodate all these possibilities. So it is max over all these max, which I can just put as max of all these terms. So each row in the upper group of expression, each row corresponds to one instruction or its group. So T plus, TI plus TR plus TA plus TR, these are coming from R class of instruction. Second line is for store, third line for load, fourth line for BQ, and fifth line for jump. Now looking at all these together now, some things can be thrown off because there are other things which are clearly dominating those. So T plus alone can be thrown off because there is a T plus plus T plus. Okay, the long expression we have for load word LW dominates the big expression we had for add, subtract, and also one we had for store word. So this reduces without any assumption to the bottom expression where we are saying it is max of three of these expressions. The first one is coming from load word and the next two are coming from BEQ, right? If all these terms, each individual factor, each individual t value was comparable, then basically let's say each of these was 1 nanosecond, just for the sake of argument, then your clock period would be 5 nanoseconds, which means 200 megahertz clock is what you can run with. Okay. Okay. Now, so this is how the things stand at the moment. We will see what we can do to improve things here, but let me just summarize now. What we observe about this is that the slowest instruction is pulling down the clock frequency or clock performance, which would most likely would be the load word instruction. The other thing which are not directly obvious, and I have not pointed them out so far, is that resource utilization is poor. We have ALU sitting at some place, but we have put 2 adders for doing an operation which ALU could have done. So question is a design possible where we don't need those extra adders? Can ALU do everything without loss of performance? So we would need to answer that question. Then the third question is it possible to do any instruction in this particular manner? Given any instruction, it may be complex, we have taken very few simple instructions. Is it possible to do all instructions in a single cycle? The answer is again no. Okay, there are some instructions which may necessarily require one to take multiple steps and go through multiple clock cycles. So if for example, if there was some instruction which reads from memory and also has to write into memory, with the given constraint of data memory with single port, where there is a single address, we can either do read or write, or in best case you can do read write but from the same address. On the other hand, if you have an instruction which requires reading from one address, doing something and writing into another address, that certainly cannot be done in a single cycle. Or complex instructions which require moving a block of data from one area in the memory to another area would require several reads, several writes. Or instructions which require in similar manner multiple operations which have to be necessarily sequenced. There is a fundamental limitation. So because of various reasons, we would need to go for a different design and try to address all these questions. So I'll close with summarizing what we have discussed today. We first of all started with a different approach to arrive at the same data path design, and the approach was basically to have several simpler design and merge them together, resolve conflicts by putting multiplexers wherever was necessary. Then we examined the control requirement of various instructions, identified the values of control signals which need to be applied, tabulated them, and came up with the control part specification as truth tables. We looked at possible way of realizing, which is that's one possible way of doing it, PLA based, and finally we analyzed the design from performance point of view, looked at how different paths are getting formed through which data has to flow, what are their implication, what is its implication on the performance, and we noticed that in this particular design approach the slowest instruction pulls down the performance of everything, and in a subsequent lecture we are going to see how to get rid of that. Thank you.